So let's see. All right. So today we're going to pick up where we left off a couple weeks back. Hope everyone's doing well. Um, there are obviously a few things to kind of briefly go over in terms of where we are and also sort of planning for rest of the semester. So as you all know that from here on out, we'll be doing all our classes online, and at least based on the feedback that I've received so far from all of you, looks like we would like to make sure at least that we have recorded lectures. And that's kind of what we will start with, at least for this week, and see how things progress. I'm happy to actually also do online lectures, in our regular time slot. If that would work as well, we can try that. But anyway, for now, let's try recorded lectures. I'll generally what I'll do is for each of our classes, each week, I'll record the lecture corresponding to the topic that we are covering. I'll make that video available online along with the corresponding notes like we've always done in the past. And then what we can do is we can set up sort of a discussion time slot where once you have had a chance to go over the video, we can get together online, either do a live chat or do a sort of a text chat where you can ask questions, and the TN myself will try and answer those as much as we can, and then of course we can set up one-on-one meetings to go over anything that's unclear. So in fact, you will notice that I've kind of updated a couple things on Blackboard, but mostly we'll continue using the website that we have for the class. I'll update those, take a look at the news section, and of course, I'll be emailing you through Blackboard as well for anything that's happening, and just so that we are all in touch. But anything that we cover in terms of class notes, class lectures, I'll keep posting them under our module section on the class website. That's where you will have access to all the material. And like I said, we'll initially start maybe Microsoft Teams. I've set up a team for our class. All of you are signed up into that team. Hopefully all of you have received an email about the same. And for each lecture, I'll create a channel on Microsoft Teams, and that's where we can have discussions and postings, anything that you can think of. And I'll set it up so that we can all share in that communication channel, so that other colleagues in the class, other students can also chime in for any particular question that is posted over there. Okay. So anyway, let's try that and see how that works out for this week, and then we'll sort of adopt to something different if this doesn't quite pan out. Okay. And again, feel free to email me anytime with any questions that may come up. All right. Now, of course, with the changing of the logistics of the class for rest of the semester, we'll have to make a little bit of a change in terms of what we had planned for various assignments and kind of the way the grading of the course was structured. So as you know, I mean, we have homework assignments in the class that basically was roughly 60% of the grade. We did have a plan to have a team project, which I think will be definitely challenging. I don't want to necessarily continue with the team project. In lieu of the team project, what we'll do is we'll just have an additional homework assignment. And the team project was slated for 30% of the class grade. In lieu of that, I'll come up with an appropriate class, individual homework assignment for all of us in the class, and that's what we'll end up doing. The other thing was, sort of doing paper presentations. I know that we did 3 of them earlier in the semester, and I don't think we'll have an ability to actually do paper presentations for rest of the term. So instead of that, for everyone who has not yet done a paper presentation, what we'll end up doing is I'll assign a paper for everyone to read. There'll be different papers, obviously, for each one of you. But you'll end up reading that paper and writing a brief report in terms of the content of the paper and sort of your takeaways of pros and cons of that approach that's presented in the paper. And I'll provide the guidelines on what needs to go in that report. As in the next couple of weeks. Okay, but we'll sort of substitute the paper presentation with something along those lines, and that will count for the corresponding percentage of the grade. All right. So with that, by the way, all of this is posted both on Blackboard. I've updated that as well as on our course website. Okay. Having said that, let's sort of recap a little bit on what we were discussing prior to spring break. If you remember, we had started talking about recognition, detection, mechanisms for doing that, and sort of the decision-making process that's involved in any of those tasks. And of course, the decision-making process is heavily dependent on the notion of a discriminative classifier, right? And we started our discussion with linear classifiers. We started taking a look at how we actually design a linear line, if you will, or a plane in an appropriate dimensional feature space, where we can separate out the positive and the negative features that we have associated with the decision that we are interested in making. We also looked at nearest neighbor, right, as a mechanism to make that decision, which was sort of more, if you will, based on the notion that we make the decision based on what exemplar we find belonging to a certain class that's closest to a new feature or example that we come across. And of course, we can generalize that to account for multiple neighbors or multiple members of classes that fall within a certain proximity of a new data point or an example that comes along. Now, I want to kind of recap a little bit in terms of linear classifiers, and then sort of, lead that into the discussion about support vector machines and what those are, and how support vector machines can sort of prove to be beneficial when we're trying to design linear classifiers. Okay, and of course, linear. I think we've talked about this. When we talk about linear, we're talking about linearity in the dimension of the feature space, right? So of course, in a two-dimensional space, linear classifier or a linear decision system would rely on the idea of drawing a line in a two-dimensional space. In a three-dimensional space, it would be a plane, and so on and so forth. But we'll talk a little bit more about that as we work through our understanding of support vector machines. So let's start again from our basic idea of linear classifiers, right? So again, taking an example, a simple example in two-dimensional space, imagine we have data points coming from two classes, okay? In this case, red data points and sort of brown data points. And we're trying to come up with a classifier that separates these two classes. And one can imagine that, we can formulate this as a simple classification system where our search is to find a separating line that separates these two classes perfectly. And here's an example of one such line, right? So we can draw a simple line, and clearly it separates out the red points from the brown points. More importantly, we can actually, define what the equation of this line ought to be in the space, right? So in the R2 space, in two-dimensional space. And of course, the equation of the line, as we have seen before, is simply given by ax plus cy plus b equals 0, where a and c essentially constitute the norm vector of this line, and b is the offset from origin as to where this line lies, in the space. So, of course, we can write this in simple matrix notation where we can take the parameters a and c and write it as a vector w. And of course, x, capital X here, would be the actual data point in the two-dimensional space, data point defined by the x and y value of where the data lies in this 2D space. So we can certainly write this as simply w dot product with x plus b equals 0, right? So that's the same equation of the line. We're just writing it in a notation so that where w, our parameter that we need to find that defines the orientation of the line, is essentially a norm vector to that line. All right, very good. Now, of course, coming back to what we had talked about earlier in terms of our linear classifier, right? If I need to define this line, basically my classifier is simply trying to solve for the unknown parameters, right? A and C in our example, right? So the vector W, such that for every positive example, let's say the red points that we have, if we think of them as positive examples, they can be written out through the equation that says, every point x sub I, which is a red example, dot product with the solution vector for the line w plus b is going to be greater than equal to 0. And of course, equivalently, all the brown points, if I look at those, when I find the line xi dot w plus b for each of the brown points will be a value less than 0, right? So we are trying to find exactly the line that will be parameterized by w and b, such that these equations will be satisfied. And that's perfect. And here's an example of what that line may result in. Of course, depending on the value of w and b, we can also end up with a line with slightly different orientation. And of course, this line also satisfies the conditions that we have set for identifying the parameters of this line. And so does this line, for example, right? So all these lines are possible solutions, including another example here. And the question then becomes, which one of these lines is actually the best line, right? So how do I know which of these solutions are perfect? Because clearly I have multiple solutions that satisfy the condition that we have set up. Now, this kind of makes us think a little bit that if I look at all possible solutions I can find that allows for the linear separation of these two classes, then is there a way for me to think about certain solutions to be good solutions while others may potentially be not so good? So one way to think about it is to say, well, if I end up with a line where closest point for that lies, in the data set that I have, if that point is too close to that line, then possibly that solution may not be the best because simple noise perturbation for a new example that comes up for that class can potentially end up being a wrong decision for the line that we have found, right? So what that means is that if we end up with a solution where the data set on which we trained to find that solution has data points that are very close to that line, then possibly that may not be the optimal solution, right? It might be too sensitive to noise or may not even generalize very well, because at the end of the day, we are trying to find this linear decision boundary based on a limited number of points. We don't have access to the entire data set, or we don't have all the possible examples that can occur that have already occurred. So we're sort of basing it on a limited data set. So as a result, that solution may not generalize well. So the counter to that, if we were to think about it, would be to say that the solution that we are looking for should be such that the distance to all the closest points to the solution we find should somehow be maximized, right? So we don't want any point, whether it's belonging to the positive class or the negative class, we don't want any of those points to be too close to the optimal solution that we find. So that's sort of one way to think about it. And that notion gives us the idea of what we call support vector machines. So these are essentially the same. They're discriminative classifiers, except they rely on the notion of achieving optimal separation of the data points that we have, right? So if you think about the example that we have here, in this case, we have, essentially this linear decision boundary that we have found. Now, if I look at sort of the positive direction from that linear decision boundary towards these red points, I see that the closest red point lies at a certain distance from the decision boundary. On the negative side, I can see that there are two more points that are closest to the decision boundary that lie on this dotted line, right? So in a way, if I were to pick this solution as my optimal solution, what I would realize is that the closest points to this decision boundary that I've found can be defined by the positive distance from it plus the negative distance from it. And this separation here, shown by this green line, is what we call the margin, right? So it's a margin between the positive and negative examples that we have while we are trying to find this optimal decision boundary. Now, the idea of support vector machine doesn't necessarily rely on accounting for all the points and computing a distance across all points, both positive and negative examples. It relies on the idea of taking a small sample of points, particularly the points that fall sort of on the closest line away from the decision boundary, both in the positive and negative direction. So in this example, the red point and these two brown points would be what we call as the support vectors associated with this particular optimal decision boundary that we are showing in this example here in the diagram. So that's the basic idea of a support vector machine. That's what it's trying to do. It's trying to find the boundary while optimizing or maximizing the margin of data points that fall on either side of that particular boundary, okay, decision surface. Now, as a result, one way to also think about it is that we are no longer trying to find only a line, but we are trying to find a hyperplane, right? So if I were to think of this entire region where we have the full line as well as the two dotted lines around it, and if I were to think of this as a plane, then what we are really finding is a plane, a hyperplane in the decision space. So we are trying to find in this example essentially a 2D plane that somehow separates the red points from the brown points. Okay. Now, so this is really what support vector machines are. It boils down to finding this line that maximizes the margin. Okay. Now, going back to our linear classification, right? So in your linear classifier, the way we were trying to find this optimal separation line was by solving essentially this parametric form, right? Wx plus b equals 0. So that's kind of what we solve for. Now, in the example of support vector machines, remember we actually not only want to solve for that decision line, we want to solve for a plane, the plane where on either side of this decision boundary, we have this dotted line. So let's say on the positive side, we call, oh, sorry, let's start with the negative side. I guess the negative side, we call it wx plus b equals -1, right? So it's a distance of 1 away from the actual linear line given by wx plus b equals 0. On the positive side, we can write the line as wx plus b equals 1, right? So each of those lines are a unit distance 1 away from the optimal decision boundary, wx plus b equals 0. So if I were to think of this, then I can rewrite my equations on how I'm able to find this particular optimal decision plane as saying that what I want to solve for is for all positive examples, I have an equation that says xi dot product w plus b is greater than equal to 1. And for all negative examples, I want to solve xi dot product w plus b less than equal to 1, right? So no point, positive or negative, should actually fall within the bounds of 0 to 1, right? So that's really what we are structuring the problem to be now. And in this example, as I said before, we don't necessarily have to account for all points in our data set to solve this. We need to only have a few points, which we call our support vector machines, right? Or support vectors. So in this example, the points I've circled, the one red and the two brown points, is really what we call our support vectors, and those will help us solve this two equations. So of course I can rewrite these two equations as sort of being one, right? So xi dot product w plus b equals plus minus 1. It just depends on what xi it is, whether it's coming from the positive class or the negative class. And as we noted, right, the distance in this case we are defining as the margin. So now let's come back to sort of take this further, right? Let's think of how we are going to solve this particular system, particular parametric form. So let's come back and look at our simple linear line in the R2 space, right? So we can write this line either way we like, right? Ax plus cy plus b equals 0, or w dot x plus b equals 0, right? Either way are the same. But now, remember, let's say we have the first support vector, right? And let's call it x0, y0, right? That support vector is going to be a distance d away from this optimal line that we have to find, okay? Now, what is the distance d, right? So we can compute that distance. So we can write it out and say that distance is really just ax0 plus cy0 plus b, right? Divided by a square plus c square square root of that, right? So that's the unit norm, because remember a and c are essentially nothing but the points or both together give us a vector, a unit norm vector with respect to the decision line. So of course I can simplify. I can rewrite this equation and write it as w transpose x plus b, right? So we are just taking the different form of the equation here. So I can write it as w transpose x plus b divided by the norm of w, right? So norm of w basically is just the exact same here, a squared plus c squared, the root of that. So now this tells me the distance of a point from the decision line that we are trying to find. So remember, coming back, right, this is kind of what we saw before. If I have a linear line, I write it as that. If I am trying to find my linear plane, all I'm doing is basically writing it in the same form, except I'm saying it has to be greater than equal to 1, right? And of course, in this case, yi being whatever is the data point we have, which will really will define whether it's a positive or negative class. So what we really want to do now is simply using the same mechanism. We are now solving for a hyperplane. We're still interested in solving for the parameters of w and b. except we are going to solve it such that for positive and negative classes, the hyperplane is defined by this particular equation, yi w dot product xi plus b greater than equal to 1. Okay. Now, let's look at our simple diagram again, right? So it's this is expanding on that form. Remember, xi dot product w plus b greater than equal to plus 1 in the event these are coming from the positive examples, right? So in this diagram, all the fill dots, it'd be minus 1 for all the examples coming from the hollowed circles. And remember, we're not solving for all points. We would like to solve for a small set of them, right? The one circled here, which will help us resolve the value for W and B. Okay, now let's rewrite this equation and say, if I were to solve for this, given these support vectors and the fact that I want each hyperplane to have a value of 1 in the positive and negative direction, right? So that should be the value that defines the closest points or the support vectors from my decision surface. Well, in which case, if I were to look at these support vectors and I say, these are coming from the positive class, coming from the negative class, what is the distance between them? Well, I can write them as W x L minus xk, right? Where let's say L is coming from the positive class, K is coming from the negative class. And since we want each one of those values to lie at a distance of 1 away from the decision surface, well, the separation distance between them should be 2, right? So that's really what it is. And if I were to rewrite all of this in the form of the equation that we have, then I would say W dot product xk plus b, of course, each one divided by unit W, minus Wxl plus b divided by norm of W. Well, that sort of simplifies into W by norm of W xl minus xk, and that should equal to 2 divided by the norm of W, right? So that's where we are. And if we think about this, basically this is norm W. So in a way it cancels out. If I were to take this guy on this side, separation distance, I sort of move the terms around, I would end up saying that the separation distance has to be half of W squared, right? So this is really what we are formulating our problem as in the case of support vector machines, which is we want to solve this quadratic optimization problem where we are interested in minimizing W squared divided by 2 such that for looking at positive and negative support vectors, we are solving the system equation which says Wi W dot product xi plus b greater than equal to 1. So that's the constraint over which we want to minimize the W squared divided by 2, right? And remember, W is really the parameter set that we are interested in solving, which is our A and C values, okay? So that's what support vector machines require. It requires us to solve this quadratic optimization to find us the optimal separating hyperplane. So how do we actually solve this? Well, typically we need to solve this by introducing some Lagrange multipliers. Okay, so we typically will define a loss function or a Lagrangian function where we will introduce an additional parameter alpha. Remember, we are already solving for W and B, but we're going to introduce additional parameter alpha and write our equation where, remember, this is what we want to minimize, W squared by 2 minus the summation of yi multiplied by Wxi plus b minus 1. Remember, we needed this equation to be, the condition was this has to be greater than equal to 1. We are simply moving that on the left side of the equation, so we can write it as minus 1. So we would basically say Wxi plus b multiplied by yi minus 1 equals 0 now. Of course, this, remember, is our condition that we wanted to solve. So we're going to add a Lagrange multiplier, alpha sub I, to each of the support vectors, yi, xi that we have. And we say, well, I need to make sure that I am maximizing this term, right? So as much as possible, all the yi's and xi's that I pick as my support vectors, they will all have a value greater than equal to 1, right? So if I take this and maximize this term, of course, I'm subtracting that maximized term from this. Then, of course, if this is minimized and this is maximized, then the term, overall will be minimized even further, right? So that's really what we are rewriting the equation as. And now we actually have to think about we can solve this because it's a quadratic term that we can solve for. Now we can manipulate this a little bit more, and if you manipulate this a little bit more, what this actually amounts to is the fact that alpha I and yi will equal to 0, right? The summation of all data points. And at the same time, the W value that we are interested in solving for will equate to the summation of all data points alpha I via xi, right? Now, keep in mind that we're not going to use all values as support vectors, right? So we expect that a lot of our alpha I values will be 0, and those will not represent the support vectors. There'll be a few support vectors that we will actually have that satisfy and fall in this condition, right? So they fall on that margin, the lines that are separated by the margin from the decision line, okay? So we write this as our dual problem, and what we are looking for is to maximize summation of alpha i's minus half of the summation alpha I into yi, yj, xi, xj, alpha j, okay? We do that in such that the alpha i's are all greater than equal to 0. And of course, the summation of alpha I yi equals 0. Okay, so that's the dual problem. So basically, we are going to simplify everything. And at the end of the day, we end up solving for essentially a revised form of the equation w dot x plus b in the form of alpha I yi xi times x plus b, xi dot product x plus b, okay? Now, of course, once we have solved this, the actual decision, when it comes time to making a decision, which is at the time of classification, things become relatively simple, right? So because we've basically formulated the function, right? We'll write that this function, right? Wx plus b. And all we end up doing is for every data point we get, we actually solve for the function and simply look at the sign, right? Whether it's a positive or a negative. So we simply make decisions based on looking at the sign of the solution Wx plus b. Now, of course, remember in the case of support vector machines, we actually rewrote this formulation to look as alpha I yi xi dot product x plus b, okay? Now, this is very important right here, this dot product, because this dot product basically is the inner product between a test point and the support vectors defined by xi. Remember, in this case, are support vectors that we actually have defined, we have solved for when we actually solved for the W, right? It doesn't constitute all the data points we have, it's only the support vectors. So the decision we are making are entirely dependent on those support vectors, not necessarily the entire set of data points that we have for the problem. So whenever we solve this optimization, it only involves computing the inner dot product, xi dot product xj, between all pairs of training points. This is very important, and it allows us to actually do something quite interesting in the event we end up not being able to find linear solutions, or the fact that our data space or a feature space is not necessarily linearly separable. This property here actually comes in very handy, and we'll take a look at why it becomes very handy when we start talking about kernel functions. All right, so let's then talk a little bit about what happens if our features are not actually two-dimensional, right? So what happens when the features are not two-dimensional? The question is, will this generalize to d dimensions, right? And the short answer is yes, it will generalize to d dimensions. All that really means is that, we are separating, or we are replacing the general notion of solving for a line with some kind of a hyperplane in the d-dimensional space. Okay, so of course, if we were to think of this in a, let's say, a 3D space, right? In which case, basically, I have a plane in a 3D space, and the plane would be defined by ax plus by plus cz plus d equals 0, right? That's the normal formulation for a plane in a 3D plane. Of course, for that plane, I would end up having a w vector, right, which is the norm vector to the plane, which would be given by the vector a, b, and c. Okay, so of course we can have a higher order equation in order to solve for these hyperplanes in high dimensional spaces. Now, everything else remains the same, right? In terms of how we actually end up solving. The distance calculation will also end up being the same, but at the end of the day, the basic vectorial form doesn't change, right? The vectorial form still remains W transpose X plus whatever the offset is divided by the norm of the vector W. Okay. And as we've said, I mean, this doesn't not limited by the dimensionality. If we have a n-dimensional space, well, that's fine. You just end up with the n-dimensional vector that you have to solve for in that particular space. Okay. Very good. So, all these properties will generalize to higher dimensions. Now, the next question is, what happens when our data is not actually linearly separable? Okay. Now, this is where the inner dot product that we were talking about in the solution form that we're looking for becomes quite interesting. So let's imagine data sets, right, that basically are linearly separable. So just in the 1D space, right? If I had these everything on a one line, right? Let's say red points and blue points. Great, I can definitely find support vectors, right? The circle blue and the circle red point will constitute my support vector, and between is my decision line that we have. So we can easily do that. Now, it's possible that our data sets will not necessarily be separable. So the below example shows that this is not linearly separable. I have 3 blue points here. On either side of it, I have red points, right? So the question is, how do I actually separate this particular data set into 2 classes? Well, and one way to think about it is that, instead of thinking of this on a one-dimensional line, what if I were to look at this data in a 2-dimensional space, right? So, let's say I create a 2-dimensional space given by x and x squared, right? So the y-axis here is simply x squared. So, these are all, remember, negative points, these are positive points, right? But x squared will basically produce both positive points, right? Either side of 0. So these will all sort of go up here. These points will end up here. And of course, I have a few points here. That scared value will end up here. Now, this becomes somewhat interesting. I possibly can draw a line right here, right? That will actually be a linear separating line that possibly separates the 2 classes. So here's that line. And of course, I have 2 red circled points as my support vector with 1 blue point circled here as my other support vector. And based on that, this would be the decision line I can draw, which actually separates this. So if you think about what we did here is we took our data points, which were in one-dimensional space. I said, well, let's project them in a higher dimensional space, a higher dimensional space where we define the second dimension to be x squared. And then in that higher dimensional space, we were able to find a linear solution that separates the 2 classes. Okay, so this is quite powerful. Here's another example, right? So let's say we have a 2-dimensional data set, right? These green points and these blue points. Well, a single line in this 2D space is difficult for us to find that will give us separation of these 2 classes, right? So on the other hand, if I were to think about this as a warped surface, right? Let's say a curved surface, right? So this curved surface, think of this as a just think of a paper, right? A flat sheet of paper, but if you actually fold that paper, it's possible that basically the two side flaps of the paper actually is where the blue points lie, and in the center is where the green points lie. Now, if that's the case, right, all we have done is taken the two-dimensional space, which was a flat sheet of paper, we curved it, and now we end up in a three-dimensional space. And in that three-dimensional space, I can potentially find a plane that separates the green points from the blue points, right? So I can actually find a linear surface again in a 3D space that actually gives me a solution to this, two-class problem. So this is very, very interesting. So the general idea of utilizing SVMs in its more general form is to think about ways where I can define a mapping function for my data points x so that they are somehow mapped by the function psi of x, where psi of x allows for the data points x to be projected into a higher dimensional feature space. Okay, so that's sort of what we want to think about when we think about finding nonlinear decision surfaces or addressing problems where a linear separation is not possible. Now, if you remember, and we go back to our Lagrangian formulation of how we are solving for support vector machines, we have the basic form that says what I want to maximize, remember, is a function, right? My loss function that we rolled initially as our Lagrangian with, remember alpha, W, and B. So let's say a generalized form, a loss function is what I want to define, and that equals to, the summation of all my CIs, right? Alpha i's, if you will, minus half of the summation over ij yi times ci multiplied by xi dot product xj. Remember, this is the inner dot product of the support vectors that we have, and of course yicj, right? So it's the so we're doing sort of the matrix formulations, right? Now, of course, this is still subject to the same constraints, right? We need alpha I, yi to be equal to 1. And of course, my alpha i's need to be greater than 0, right? So they're bounded by some upper bound. Now, this is the Lagrangian formulation, right? But over here, in this inner product defined by the support vectors, right? These are the support vectors in the original feature space, but I can actually also think of them as transformed support vectors into a higher dimensional space, right? So I can rewrite the exact Lagrangian formulation where instead of xi dot product xj, I can write it as psi of xi dot product psi of xj, right? So where psi, remember, is my transformation function that allows me to take xi into a higher dimensional space. So, of course, nothing changes in terms of classification. Of course, when you do want to classify under a solution that you find, you're going to have to apply the same transformation function to a new data point that comes in, so that we are able to find the appropriate solution and look at the sign in order to make the decision during classification, right? But this is post training, right? This is only applicable when we already found the solution. During the solution finding, this is the equation that we need to solve for. So, of course, what kind of transformations can I think of, right? I mean, there are all kinds of transformations I can think of, right? So I can take a two-dimensional vector, let's say, x a point given by, two coordinates, x1 and x2. And I can say, well, let's define a transformation function psi that basically is given by a six-dimensional transformation. I can write it as 1 x1 squared root of 2 x1 x2 x2 squared root of 2 x1 root of 2 x2, right? So this is one possible transformation. Of course, if I were to apply this transformation, well, great. I can take the dot product. Remember, it's the inner product that we have to take when we write it in the Lagrangian formulation. So, psi of xi transpose psi of xj. Of course, this I can expand it. If you basically take the two multiplications, you expand it, this is what you would end up with. And it simplifies to this form, 1 plus xi transpose xj whole squared. And this, we write it as, k of xi xj, right? So it's the same thing, psi of xi xj or k of xi xj. It's k is typically what we call a kernel. So we end up using k quite a bit in lieu of, separately writing psi of x and psi of xj. Now, this particular transformation function that we just wrote here, we call this the quadratic kernel, right? You can have other kinds of kernels that we can write. You can have a polynomial kernel, right? And a polynomial kernel will be defined by the degree of the polynomial, right? So it would be x transpose y plus c to the power of d, right? So if I'm looking at let's say a cubic, d would be 3, right? So it would be a third degree polynomial that would constitute your kernel function. You can have other kernel function that you write, typically things like sigmoidal or Gaussian, like a radial basis function, and so on and so forth. Now, in general, doing this transformation where we take our data points and project them into a higher dimensional space using a kernelized function, we call it the kernel trick, right? So the ability to take support vector machines, which by definition are finding a linear separation hyperplane in our feature space, making them amenable such that they are able to find nonlinear decision boundaries is possible through the kernel trick, right? So this kernel trick is very, very important. It allows us to now take classifiers and generalize them to be able to solve for nonlinear decision boundaries. So this is a very, very important property and is used extensively, of course, in support vector machines. But as we'll see later on, this is also something that can be used for other kind of classification systems. But this is an important trick to keep in mind. So there are, a variety of kernels that have been used, in practice. Linear, of course, is, a very simple kernel. It's simply xi transpose xj. So you're not doing anything else. You're just, taking the product of the two elements. A polynomial like we looked at, right? So polynomial to a degree p, whatever p needs to be. Another function is the Gaussian, or often referred to as the radial basis function, which is the Gaussian form, right? So it's the exponential negative of xi minus xj whole squared divided by 2 sigma squared. Of course, sigma will be a parameter. It's a value that we typically have to work with. I mean, it's a modulating parameter to define the extent of the basis function that we're defining for each support vector. Now, so this is a very important property and an ability to solve sort of nonlinear feature spaces. Okay. Now, of course, the final question, and again, this is not a new question. We looked at the same question in the context of linear classifiers as well, which is what if we have more than two categories, right? So in all this discussion so far, we've talked about having two classes that we need to separate. But obviously, in real life, there might be situations where you have more than two classes. And again, there is the notion of multi-class support vector machines. And the solution to that is very similar to what we have looked at when we talked about linear classifiers. So if I do want to solve for multiple classes, Well, one possible way is to by combining a number of binary classifiers, right? So again, looking at the one versus all strategy, which is we learn a support vector machine for each class versus rest of the classes, right? So we are really making a decision around one class at any given time. And of course,